Well, thanks very much, David. Thank you. And thanks very much to Finding Petroleum, to inviting us in again to talk about another one of the world's more interesting hydrocarbon basins. And there's actually two reasons why I'm really excited about doing this presentation today. Is first, of course, because in an illustrious crowd of good presenters and a fantastic audience. And the second is, in the words of that great Welsh poet Max Boyce, to say, I was there, ladies and gentlemen, because we're here at the time of the next Lebanese license round. In fact, it's the first Lebanese license round. It's a really exciting time. A huge swathe of unexplored continental crust just brimming with hydrocarbons, and that's what I'd like to talk to you a little bit about today. So, first off, I guess the motivation for talking about it is that Spectrum, who I work for, have a significant seismic data set in the Mediterranean, both in the Western Mediterranean and the Eastern Mediterranean. We've been in the Eastern Mediterranean for, I guess, maybe 14 years, acquiring first regional seismic, and that regional seismic kind of keyed the industry into the exploration potential of the Eastern Mediterranean. And at the time that it was acquired, in water depths over 2,000 meters, it was visionary seismic for anybody to be acquiring data in there, because in those days it was really difficult to drill in that sort of water depth. Only a few companies had that capability. And to acquire a big regional data set to look at the Eastern Mediterranean, I just think was brilliant. Working from that through the years, we've acquired other data sets, some after initially acquiring in deep water right out into the Hodgson Basin. We acquired some data quite close to shore. And the most exciting thing is that recently we've just acquired our first 3D seismic. And it's this 3D seismic which is I guess the focus of the talk today, as to the rationale behind why we chose that area to shoot seismic in, and why on earth we would conceive that it might be prospective. So I'll just briefly talk about the 3D, and then we don't need to come back to it. What we acquired was the 3D seismic survey. It's about 3,000 square kilometres of 3D, and we acquired it using two vessels. Firstly, the Polar Duke was a dolphin boat, and secondly, in this part down the south, Fugro's Geobarents vessel. The acquisition was just a dream, really. We managed to acquire in the order of nearly 80 square kilometres a day. There's beautiful weather, beautiful wave height, and in fact, if you look at the currents in the Mediterranean, there's some nasty old currents along North Africa in the Mediterranean, but here in the Eastern Med, it's very calm, very few currents, so acquisition was a dream. And we acquired, I think, quite good quality data, and we're going to have a look at that in a little while. But the most revolutionary thing that's happened in Lebanon of late is that they have completely got their act together with regards to the hydrocarbon exploration business. Previously, things had been moving very slowly in Lebanon, because all of the steps that you need to go through to have a license round and to get the legislation in place had to be discussed and agreed by the Council of Ministers. And so it's like going to Parliament every time you want to talk about the smallest detail. But then in the back end of last year, I think it's the 7th of November, they consolidated and formed the Petroleum Administration in Lebanon. And what that means is that each of the complex factions that control power in Lebanon had a seat on a small body that was totally responsible for getting a license round in place. So they had 7 places, including that of the minister, and each of the department heads had to be from a different sectarian group. But they come together and they have totally got control of the hydrocarbon exploration process, so much so that on the 27th of December last year, they announced the forthcoming license round. So the timescale was on 27th of December they announced the license round. They've started the pre-qualification submission process right now. By the end of March, they'll announce which of the companies that have attempted to pre-qualify have got through and are on the short list who can bid then for blocks in Lebanon. And the bid round opens on the 2nd of May. It's really exciting and fortuitous timing for us because our seismic data will all be ready by the end of March. The whole 3,000 square kilometres will be ready, processed through PSTN at the end of March. So good timing for us and an incredible acceleration of activity offshore Lebanon compared to what had been previously achieved over the previous couple of years. So pre-qualification, I'm sure there are plenty of us in the audience today will be looking at this for pre-qualification. They've got 4 areas that they want people to pre-qualify within. Obviously, you have to have a legal entity, financial, some small criteria that might be of interest to some of us here. If you want to be a deep water operator, an operator of a group, then you've got to have assets of about 10 billion US dollars. So that's, I guess that's most of the retired BP people that you were talking about earlier on. And then if you want to be a non-operator, then you only have to have assets of $500 million. So that's okay. In terms of the technical side of things, if you want to be a deep water operator, you've got to have some track record of exploring in deep water. And if you want to be just a partner, then you just have to have some relation to the petroleum industry. So that's what they've set out as their objectives. Because we haven't been through this process yet, we don't know if you don't meet one of those criteria whether you'll fail or not, but those are the objectives for the pre-qualification. And what it means is that the government of Lebanon are specifically looking for someone or companies that will come in and start drilling immediately. That's really bold because they've never had a license round before. The whole of the offshore acreage is unlicensed, and what they want is for a company to come in and start drilling immediately. How can they do that? The reason they can do that in offshore Lebanon is that they have acquired 3D seismic over most of offshore Lebanon. About 70% of offshore Lebanon has had 3D acquired on top of it. So we've already got through the first phase that we normally do when we pick up acreage somewhere unexplored, is shoot some seismic and then think about it for a bit. Got through that bit, we can just march straight into drilling. So the question for us now, I'm not going to talk about seismic anymore. The question for us now is, what's the fuss? Why are we bothered? Well, the reason why we're bothered is that offshore in the southern Levant Basin, offshore Israel, in 2009, a momentous discovery was made, the Tamar discovery. It was made by Noble Energy, and that began a tsunami of discoveries in this southern Levant Basin, which has, since 2009, proved up over 30 TCF of gas, and the numbers being bandied around about 50 TCF of gas. Most of it is very dry gas. In fact, it's quite remarkable how dry the gas is. And Noble have said, on the basis of isotopes and the fact that it's very dry gas, they say that it's probably biogenic gas. So, at the end of this process, the industry looking at the Eastern Mediterranean can only conclude one or two things. One is that this is a dry gas province. Two, that it's mostly offshore Israel, because we can see it is. Three, that there's a trend of discoveries that goes, in terms of as it was made chronologically, it went Tamar, Dalet, and then Leviathan and Aphrodite. So there's clearly a trend of discoveries running from the northwest to the southeast across the region. And the last thing that the industry can conclude is that this basin is pretty much licensed and is pretty much drilled up, so not much for anybody else to have of interest. Well, in fact, all of those things are not right. And so we're going to start by looking at them all one by one and figuring out whether there's some other prospectivity in the region. First line I want to show, I'll keep coming back to this line because I just love it. It just excites me so much. It runs from the south to the north, so offshore Israel goes across the Tamar discovery, and then it runs directly north into offshore Lebanon. The border between Israel and Lebanon is somewhere around here, and into the northern Levant Basin. And it just shows so much about this region that is really exciting. So here's the Tamar discovery right here, and the horizon that contained the 8 or 9 TCF of gas in Tamar is in the early Miocene. So that's between the orange and the yellow horizons, in the earliest part of the Miocene, and sitting just on top of the Oligocene here, and the upper Miocene sits just on top of that again. Now, the first thing that we can do with this seismic line is that we can take that early Miocene package and run it to the north, and you can see that it just about trebles in thickness. So, in fact, on the southern Levant area, just here, it's actually quite a thin sequence of early Miocene sands, and as we run to the north, that whole section really thickens up into the northern Levant Basin. That's really interesting. What's happening is we're going from the southern Levant area across what we now call the Levant Ramp, after coined by Alan Taylor, the Levant Ramp here, and then into the deeper northern Levant Basin. So we're going across a structural lineament, and the effect of it is it goes from a relatively thin sequence in the early Miocene to a great big fat sequence in the northern Levant Basin. Now, the next thing to look at is these bright events in here. And what we're seeing here, although you can see hydrocarbons in Tamar, you can map the big flat spots. But what we're really seeing here is that we're seeing coarse clastics, we're seeing sandstone. So when we look in this package here, you can see that the early Miocene sequence is quite sandy across the southern Levant Basin, offshore Israel. And when we come to the north, into the northern Levant Basin, you can see it really thickens up. So whereas we might find 200 meters, perhaps 250 meters in Tamar, big deal, because there's 1,000 meters of sand in the northern Levant Basin. Really exciting just seeing that. That's quite interesting in itself. How does that happen, and why does that happen? Well, the previous model, previous to Tamar being drilled, the idea, I think, was that sands were coming off the Arabian plate and across into the Levantine Basin from the east. And as time's gone on, and this area here has been completely covered by 3Ds, and we've gone right up to the border with Egypt, we find that that isn't the case, and that these sands aren't coming from the Arabian plate at all. They're not coming from Israel. They're coming from the Nile Delta. These are early Miocene sands, and they're pouring out of the Nile Delta as part of the many early Miocene channel systems that were coming out of the delta at that time. A recent presentation by GTEC showed basically the fetch, or the provenance of the sands in the Nile Delta, and it's a huge area. The Nile was draining a massive area in the early Miocene. It was all pouring down here and then being deposited in huge deep water transport systems into the Mediterranean, both across to the west, where BP made their big discoveries of Raven, to the north into the Temsa, and then to the west, Temsa Aachen maybe, and also across the Levantine Basin through what is now the Tamar Leviathan area, heading in this direction here. So that's the model for where the sands are coming from. So what we're seeing across the southern Levant Basin is actually the transport system. We're actually seeing the channel systems that are taking sands from the Nile Delta specifically to drop them into the northern Levant Basin. We've got plenty of analogues around the world for transport systems of this size. If you go to the Pab Ranges of Pakistan, you can walk around systems of this size, this magnitude, where you go from channelized systems into turbidite fan systems that over hundreds of kilometers. You can walk around with a hammer and you can hit it, and you can really believe that these systems work on this scale. to illustrate this is Dave Peace has illustrated this, showed it at PETEX. I thought it's a really neat example. This is the lower Miocene, the early Miocene surface in time for this area. There's Tamar and Leviathan down here, and this is the northern Levant basin, so it's much deeper at that time. And the model here is, although there may be small fans coming in from Israel, they are tiny little fans. Mind you, it does make you wonder what's in them, because all along this margin you might find fans coming off Israel and Lebanon. But that material will be, eroded, basically eroded limestone scarps. It's going to be some ghastly carbonate conglomerate, and that's, to be quite honest, the last thing any of us need. So what's really happening is that the big channel systems are coming in from the Nile Delta over here, and they're moving across the southern Levant basin, and they're dumping out into the northern Levant basin. Now, the first and probably the only note of caution I'll mention today is that it is a bit deeper in that northern Levant basin. So in Tamar and Leviathan, the sands are about 3,000 metres below the mudline, whereas by the time we get into the same sands that we see in the northern Levant basin, they'll be about another kilometre deeper. So I don't think that's actually going to be too much of a problem, because the sands in Tamar and Leviathan are in the order of 25-26% porosity. By the time we get into the northern Levant basin, you're looking at sands at maybe 20% porosity. That's not a big deal, really. So here we go back to that original seismic line, the one running north-south, illustrating the transition from the southern Levant basin into the northern Levant basin. You can see that the sands, you can really see them thickening up here, and they're going from channelized systems in the south and into deep water turbidite fans that are effectively prograding into the basin, these turbidite sheets into the basin, moving north. It is interesting about the structure of Tamar, because Tamar, as you notice on this line here, is this wonderful little anticline here. It doesn't look faulted at all. That's because we're looking in the direction that shows that property to its utmost. If we look in an orthogonal direction, it's faulted to bits, and I'll show you an example of that. But the thing is that the formation of Tamar structure is the inversion of a Syrian arc anticline. So what we basically have is a tilted half-graben in the Jurassic and the Cretaceous that gets inverted in the early Miocene. And as the sands are coming across the southern Levant basin in the early Miocene, they get kind of channeled into these half-grabens. So the synform where the half-graben was is where the channels tend to be. And then when you invert the half-graben, then you find that the best sands are in the inverted half-graben, if that makes sense. In fact, the timing of the inversion is in the upper Miocene. It's a key point, and we'll come back onto that when we talk about structure. So within this Syrian arc inverted anticline here, we'd expect to have good sands. Outside of the Syrian arc anticline, then you expect to have worse sands, maybe thinner and perhaps more silty, not quite so good quality. That's just not the case when you come to the northern Levant basin, because these are just big turbidite sheets. So it's important to be able to map out these turbidites and map out the reservoir architecture within the turbidite sheets, but you're not going to have little constrained good sand bits and separated by poor sand bits. So the next thing, what I should say on this one, the next point to start talking about, once we've got comfortable with the fact that here there's a kilometre of reservoir compared to the measly 200 odd metres of reservoir over here, the next thing to get comfortable with is the source story. Now, what's intriguing about all of these discoveries at Tamar, Leviathan and so forth is all the discoveries that appear to be in the early Miocene are all biogenic gas. So no thermogenic gas at all. There is one well, one of the Leviathan wells that have been deepened, we think, into the Oligocene, and once they deepened that well, they didn't actually report what they found. Noble started talking about condensate and liquid yields after they'd done that. So there's a sniff of thermogenic hydrocarbons in this area, but not in the early Miocene. So we did some 3D basin modelling to try and figure out why that might be. And if we look at the top Oligocene depth map here, this is the Tamar, Leviathan, Aphrodite. This area here is actually relatively shallow today. And when you look at the heat flow measurements that have been reported, then it seems very likely that this whole area here is just not mature, even for oil generation today. So this whole area here, the Oligocene source rock, is not mature for thermogenic hydrocarbon generation. Well, it's no wonder it gets munched by microbes and we generate a lot of biogenic gas. However, as we go to the north, into the northern Levant basin, as you go across the Levantine ramp just here, into this deep basin here, it becomes brilliantly mature. And in fact, ever since the Mycenaean, so over the last 6 million years or so, the Oligocene source in this area here will have been generating oil, and that oil would have been migrating. So this was the conclusion, I guess, of our 3D basin modelling that we'd done, was that for the last 6 million years, the Oligocene source rock sitting right underneath the early Miocene reservoir has been generating oil. Oil's been migrating up hopefully into the structures right above it. Well, that's quite interesting. There are other source rocks. I mean, it is a slightly more complicated system that we're talking about, and there are other potential source rocks in the Jurassic, in the Cretaceous, in the lower part of the Tertiary, in the Eocene. All of those might work, and they might be generating gas. The only issue that they've got is that they've somehow got to get through the Oligocene before they get to the Miocene, the early Miocene sands. So that might be a bit tricky for them. However, we'll come on and we'll talk about perhaps some evidence that some of this is happening in the basin as we go on. So we've done some basin modelling with a company called Stratachem, but no reason why you'd want to believe us. Basic FranLab, who are a sort of independent body, did some work for the Lebanese government, which has been published again on the Lebanese government website. And they looked at all the seismic data across the whole basin. They did some really complicated basin modelling, which is quite phenomenal, really. But no surprise, what they found was that the basin epicenter, which is located just here, is where the source rock is most likely to be mature. So no rocket science there. They also suggested in this area there might be a lot of biogenic gas. Well, there's probably 50 TCF of biogenic gas, no more than a stone's throw away from it. So again, no rocket science comes out of the box on that estimation either. The other thing that they said was that this probably is an oil source that's working in the basin. Well, that's really interesting, because about 10 years ago, there was an SAR, a synthetic aperture radar survey carried out in the Eastern Mediterranean. They found loads of natural oil slicks. So, yep, there is a working oil system in the Eastern Mediterranean. You don't have to involve any rocket science for that one either. And here's some examples of some of the seeps that have been seen. A company called Astrium, I think, is currently producing and selling that report of the oil slicks in the Eastern Mediterranean. But where are they? Oddly enough, all the oil slicks turn up along quite close to and along the parallel with the coast of Lebanon. That's where most of them turn up. I have to say, not all, but that's where most of them turn up. So does that mean then that it's only here where the oil slicks turn up that there's a working oil source? Well, no. The reason that there's a whole lot of oil seeps along this margin here is because of the Mycenaean salt. And so if we look on this seismic line here, this top section here, which is 1.5 kilometres, nearly 2 kilometres of salt in this area here, is right over the basin epicenter. And what happens is that oil, excuse me, oil is generated from the Oligocene. It wanders up and gets stuck underneath the Messinian salt, and then it migrates its way along to the edge of the basin. Anywhere it can find a little break through the salt, or where the salt finally pinches out, that's when the oil gets through, and then you start to get the natural oil seep. So it's no surprise at all, as the Messinian is very thick over here and very thin over here. It's no surprise that you find the oil seeps right the way along here. So the location of oil seeps tell you that there's a working oil system. We know that. And if you're a proper seepologist, you would say if you can see oil seeps, then the oil must be being reservoired somewhere. So there's oil reservoirs as well. But what it doesn't tell you is exactly where the oil is being generated, and certainly not where it's being trapped. Right. So we've dealt with, effectively, reservoir, and we've dealt with charge. So the only thing we've got to worry about now is structure. And what is quite clear is that in the southern Levant Basin, you've got big structures that are very simple. These inverted Syrian arc anticlines are very straightforward structures, not complex, and they're very big, and everywhere else it's really complicated. Well, when you come into the northern Levant Basin and you look at this seismic line, you see all these faults in here, and you think, well, it does look a little bit complicated. But actually, nothing could be more far from the truth. And I did a little comparison here. These two seismic lines are on the same to a time scale as well as the same spatial scale. This is a line from the northern Levant Basin across one of our bigger prospects that we mapped on the 2D called Hyperion, and you can see that it's hardly broken by faults at all. It's a very gentle structure. The whole feature itself has about 150 odd meters of relief, so it's not totally without structure, but it's very, very little fracturing, very little structuration. Similarly, or rather not, to the south in Leviathan, we have the same seismic line going across the Leviathan structure. This is 20 TCF of gas being found by Noble here, but it's very, very complicated, and it's no wonder. These are inverted Syrian arc inversion features, and they're very complicated, often very tight, lots of tectonism, lots of complex faulting. So in fact, in northern Levant Basin, you've got simpler structures, but the thing is, are they going to be as big? And that was the thing to try and map out. So based on the 2D data that we had, we did a structural map. This is in time, but it's a structural map of the early Miocene in the northern Levant Basin. And what we found was some absolutely huge structures. There were stoters. Hyperion here is over 100 square kilometres, and we've got some smaller ones in the range of 30 to 40 square kilometres, which, when you apply some quite conservative estimates of reservoir, saying that perhaps we might find 100 metres of reservoir across this area rather than 1,000, then you come out with some quite big numbers for reserves. And so for a structure like Cronus, which I've mapped here, this guy, Cronus, is here about 3 TCF in this estimation. It's actually not far from the same size as Tamar, which is known to be 8 TCF, so I might have got my hydrocarbon potential estimate wrong by a factor of 2. Never mind. The point was that within the area that we were going to shoot our 3D, which is this purple area, we had the potential there for 20, who knows, maybe 40 TCF. It seemed like it was worth doing. The key point with 2D data is that you can't really trust it when it comes to mapping these structures. And so what we needed to do was to shoot 3D to make sure these structures didn't disappear or change shape or get smaller when we do our next set of evaluations, which is an evaluation of the actual potential of the fault blocks themselves. And the one thing that kind of weirded me out about this structure map that we'd made was that it looks like someone's taken a piece of glass and just dropped it on the floor. You've got these fault systems, they sort of wander off all over the place, and it does seem rather strange. Well, with 2D data, it's obviously very easy to alias your faults, so it's very easy to get it wrong. So although we can use our 2D data to sort out a reservoir story and a hydrocarbon charge story, we need 3D data for the structure. So we went and shot a 3D, 3,000 square kilometres of 3D, so that we could image the structure properly. And this is just a view of the volume, and you can see that you can image the faults extremely well. This is the early Miocene down here, and the upper Miocene up there. So first off, this is a east-west line, effectively an inline across the region, and these were two of the structures that we could map on the 2D very clearly, and we could map them even better with the 3D, but more so we've got fantastic resolution on the sands that we've got in this package down here. And we also see another package which I hadn't even dreamed of before, and that is up in the upper Miocene, just below the salt. You can see another clastic package in there, and that's given us another play fairway that we didn't even dream of based on the 2D data. But again, the 3D data was really here to map the faults. And the reason why we needed the 3D data is that in the crossline orientation, so virtually north-south, you see that there's a lot of faults, a lot of these tilted fault blocks, and you've got to map these guys out properly to make sure that they really do map into closures. So just a small trick that I'll let you in on is that this event here, which is really easy to map, is the top of the early Miocene, and it's really just a proxy for the lower Miocene sands. So far we haven't had the data long enough to map the lower Miocene sands out properly. We will do. So what we've done is just, excuse me, we've run around and just mapped the structure based on this early Miocene event. And what we find is that not only do we find that there are structures there and that they're big structures, but we find more of them. It's always good when a 3D does that to you, and slightly rare, I have to say. So this is a time map of the top of the lower Miocene in our 3D area, and it shows quite extraordinary features. These faults here are very straight, and when you look at them in section, they're also very straight in section as well. And they're quite odd in that regard. They're not listric faults at all. They're just straight, what have been called piano key faults. And a good analogue has been found in canyonlands in Utah for these straight faults. And you can see that the structural pattern here is very, very similar to the structural pattern that we're seeing in the 3D area. Now, the reason why Canyonlands works this way is that these extensional faults here soul out in, well, effectively salt. So they soul out in the salt, and the salt basically just squidges around and accommodates all the space problems, which makes you wonder about the Oligocene down here below the early Miocene sequence in here. This must be very plastic. It must be very easily deformed, because it's just taking up all the space problems that are formed from the extensional faults that are right above it. And these faults just soul out in this unit. Well, I think the reason that it's so plastic is that it's a rather lovely source rock, and it's been mature for hydrocarbon generation. It's full of oil, except for the oil that's expelled out of it already. And so that's why it's such a plastic formation. So let's look at some of these structures. So these are the same structures that we could map on the 2D, but now, of course, we can map them perfectly. There's no aliasing of the faults. We can just map these structures out. Not even I can get this wrong. And what it shows is something I didn't really expect before, and that is in the western side of the area, there's a very long arch. It's a one single feature that has been broken into a series of fault blocks, and you can see that arch running through here. In fact, there's another hint of an arch here, and across the area there are more of them. So what they're showing is that these are actually folds. They're very straight folds in an east-west direction. It's a compressional event that's happening at exactly the same time as the extensional event is opening these features here in a north-south direction. Structural geologists' dream or nightmare, depending on your point of view, I guess. But for us as explorers, it does something really wonderful. This long arch on the western side of the structure actually closes. It's a basin centre massive closure with about 800 square kilometres of time closure. And when we depth convert this, it just pushes this area here down, pushes it down, so it just makes the closure even stronger. So you have this huge closure in the basin centre, as I say, about 800 square kilometres of closure with these fault blocks within it. And as an explorer, you don't get these opportunities very often to have a playmaker type of success. So you drill this guy here, Cronus, and you find yourself 4 TCF, you feel very pleased about it. But how can you not find more gas here and here and here, or oil here or here or here? How can that work but not the other ones? That's the question. So this is the potential for huge playmaker success. And it sounds a bit like an explorer's dream, that one. But when we look just 70 kilometres to the south, and we look at the early Miocene on the southern Levant Basin, you've got Tamar, Leviathan, Aphrodite, Dalit, Tannin. It just goes on and on. You have that playmaker success. So there's no reason why it won't happen again within this overall basin closure. It's not the only closure at early Miocene level. There are plenty of other ones here and here across in the eastern part of the 3D area. But there's one feature that is really, really exciting. And that is this guy here. It's called, I call it Oceanis, which, one of the bigger titans. And it's a really interesting feature, and I want to show you it. The reason why it's really interesting is here we are down in the early Miocene. It's the only feature we've got like this in the 3D area. It has 1 kilometre of throw. It's extraordinarily steep. Everything else in this area has, the relief on these prospects is like 400 metres or so. There's one structure which has 1,000 metres of relief on these late inversion structures. And above it, you can't see too much on the seismic above it, but it deforms the base of the salt, and then there's all this deformation through the salt, and then there's gas chimneys and pock marks on the seafloor, which are bright when you look at the amplitudes. And then we went back to Astrium and said, well, do you see any oil seeps out here? We shouldn't expect to see any oil seeps out here because all the oil seeps are up close to the coast where the Messinian salt pinches out. And they looked at this area where we shot our 3D and they said, no, it's covered in oil seeps. And it gave us a few examples. They haven't told us exactly where yet, but we're working on that. But it would be really unsurprising if above this pockmark we actually found natural oil seeps. So we have a way of communicating through the salt. Now, this is really fascinating because you have to ask, how do you do that? How do you bust through 1 kilometre of salt? That's not a straightforward thing to do. The only way I can think of doing it, apart from accessing some deeper, super overpressured Cretaceous or Jurassic gas source or something like this, of which we see no evidence for when we look at the Turonian underneath here. There's no faults or anything like that that we can see. The only way I can think of doing it is to have 1 kilometre or 1,000 metres of gas column, and at the top of that gas column you build up such a big pore throat entry pressure, in goes the gas. It forces its way up, and then it has such an overpressure that it's punching its way through the salt. So that to me says, wow, this could be evidence for a big gas column. It's really exciting, but not exciting for Oceanis. I wouldn't go near that with a drill bit, but because the likelihood is that thing has probably popped its lid and the gas is gone. But the thing is, if we can stick 1,000 metres of gas column in Oceanis here, how are you going to keep it out of this one and the others? They're all going to be full of hydrocarbons, so it's really exciting. Yes. In conclusion, he says, lying through his teeth. I'm almost there. I'm almost there. Just want to show you one more play. This is in the upper Miocene. We've looked at the early Miocene. Now let's look at the upper Miocene. We didn't even dream that this had potential. When we look at the base of the salt, we map that out. We find that big ridge again. We find that big old structure. And when we map that out, we've got nearly 200 square kilometres of structure, and it's really easy to map out. It's really shallow, and it's all sorts of stratigraphic pinch-outs onto these upper Miocene inversion structures. So lots of potential. So, almost in conclusion, penultimate slide. What's the 3D give for us? The 3D allows us to map out the sands. It allows us to understand the transition from the regional story based on 2D into the 3D. It allows us to look at the hydrocarbons on the using the seismic before we drill. We've only done provisional work so far on the 3D area, but I'd never heard a geophysicist use the word stonking in reference to AVO anomalies before. I'm not sure what it means, but it sounds exciting. And the last thing that we can do is that we can map these structures, map their size out, and we find that they're really big structures. They're bigger, simpler, less complicated than the ones in Israel. And so, in conclusion, then, the 3D reveals that Lebanon is going to be the next hot place in the planet. It's time of the license round, and it's time for companies to pre-qualify. Thank you very much.
I don't know whether Alan Williams is in the audience. I don't think so today, but his view would be if somebody shows you a picture of oil seeps, you need to go and hire a rowing boat and with a couple of jam jars and go out and sample the seeps and figure out what's in them. Apart from time for facetious comments like that, we don't really have time for questions, I'm afraid. So thank you, Neil. Thanks for that. And